Hi, and welcome back to the Implementing and Administering Cisco Solutions to CCNA 200-301 video series course by EC Council. My name is Glenn Singh. In this video, we are going to take a look at interpreting the routing table of a Cisco IOS router. So let's dive on in. Within a Cisco router, you will find a routing table. The routing table contains a list of paths to all the destination networks that are known by the router. Each of these paths are what we call routes or network routes. For each route that is installed within the routing table, a routing protocol is actually assigned to it. Now, the routing protocol code simply indicates the source of the route. So what does this mean? Well, the routing protocol simply tells us how the router learned about a particular route to reach a destination network. Within the routing table, there are many different codes, and these are some of the main codes that you have to know as a network engineer. So, C means it's a connected route. A connected route is directly attached to a router. We have L, which indicates a local route. We have S, static route. R, which indicates routing information protocol. And R, or well, to be specific, RIP, is actually a very old dynamic routing protocol which was created back in the 1980s. Then we have O, which indicates OSPF for Open Shortest Path First, which is one of the most popular dynamic routing protocol which is commonly used in today's networks. There's D, which indicates Enhanced Interior Gateway Routing Protocol, or for short EIGRP. EIGRP was a Cisco proprietary protocol up until 2013. So 2013 and prior, only Cisco devices used EIGRP. And EIGRP, of course, is a dynamic routing protocol. There's another code which is EX, which means it's an external EIGRP route. And we have B, which indicates Border Gateway Protocol, or BGP. BGP is actually a dynamic routing protocol which is used to route, guess what? Route the internet. So BGP is what internet service providers actually use to exchange dynamic routes. But we will discuss these further as we go across or go along domain tree. On a Cisco router, to view the routing table, we use the command show IP route. And once we use the show IP route, we'll see all the codes listed here. But you still need to know the essential codes. These codes, as mentioned, simply indicates how a route was learned by the router. So to put simply, if we see a route and the code is S, it simply tells us that that route is a static route. How about if we see, let's say, a route that has a code O? Well, O simply means, hey, this route was learned by the OSPF routing protocol, and that's how it actually got installed within, well, our tree routing table. Within the routing table, there's a terminology known as the prefix. The prefix in the routing table, to be specific, it's actually the network address. However, in the routing table, the prefix is the actual destination network. So let's take a look at what the prefix is, or to be specific, the actual destination network. In this snippet, we use a show IP route command within our tree. It gave us all the routing protocol codes, and take a look at all of these entries that are highlighted in yellow. These here, each of these are what we call routes, like the entire line. So for example, let's take a look at this here. This here is actually a destination route, or to be specific, it's just a route. And these highlighted network IDs, these are actually called destination network. So within the routing table of a router, the routing table only contains destination networks, and an entire line is actually called a route. So to put simply, let's take a look at this entry here. Well, right now, this network is a directly connected route. So we are on R3. So if we have to draw this, let's say for example, this here is the R3 router. Well, we've seen here that 192.168.10.4/30 is directly connected to serial 000. So what does this mean? Well, let's say this here is a network, which is 192.168.10.4. And this here is /30. Well, to put simply, it is also saying that this destination network is directly connected to serial 000. So this here is a network. Let's attach a serial cable, which is this zigzag line. And this interface here is serial 0/0/0. Well, 0/0/0. So this means that if any packets enters router 3 that has a destination, and let's say the destination is .5 or even .6, well, 192.168.10.5 or 192.168.10.6, well, router 3 is going to look in the routing table starting from top to bottom for a direct match. Now, the routing table usually contains destination network addresses or destination network IDs, and it will check the ranges of each of these network IDs and determine whether .5 or .6 exists in any of these. So to put simply, the router is going to check the routing table from top to bottom each time it has to perform a lookup, and it will find, or it will look for a match in terms of a destination network, such as this network here. Once it finds a match, it will stop processing. Well, it will stop searching downwards and will continue to process this route. So it will say, okay, this route is directly connected. This here is a destination network, which is 192.168.10.4/30, and it is directly connected to serial 000. So, therefore, router 3 will send the packet out of this interface, which is shoot the packet out of here, and .5 and .6 is located here. And that's exactly how the router actually performs its lookup. It goes through the routing table from top to bottom, searches for a match. Once it finds a match, it will process that route. It will check the destination, or well, I won't say destination, but the actual exit interface, which is the interface is sent out of, and forward it out of that port. Another key component is a network mask. The network mask is also called a prefix link that is used to represent the subnet mask of a network. Well, I think you are very familiar with this because during Domain 1, where we discuss IPv4, subnetting, and network prefix, we discussed the prefix link there. So let's take a look at where we can see the network mask. At the end of each of these network addresses, you will see a slash with a number. And if you recall from Domain 1, we discussed this slash is called the prefix link. But in the routing table, they call it the network mask. So, example, a /24 simply represents that there are 24 ones in the subnet mask. And if we convert that 24 ones from binary to decimal, we'll get 255.255.255.0, which essentially is a Class C subnet mask. Look at this one down here. This directly connected network is 192.168.10.8, but it is a /30, which means there are 30 ones in the subnet mask and 2 zeros at the end, therefore giving it a total of 32 bits. and converting those 30 ones from binary to decimal, we will get 255.255.255.252. In other words, a /30 subnet mask. A very important component is called the next hop. The next hop is simply the next hop IP address, or in other words, it's a next router in line to forward the packets. So this sounds a little confusing. Let's take a look at what exactly the next hop is in the next slide. So let's take a look at this routing table. So again, we're on router 3 and we have 3 OSPF routes. So if we were to draw this network, so let's say for example, we have our router 3 here, which is our router right now. And let's take a look at this third network here, which is 192, actually is 172.16.3.0/30. And we could see that this network is via 192.168.10.5. This timer simply indicates how long the route has been installed in the routing table, which is currently 1 second. So as long as the route is installed in the routing table, this timer will increase. And we can see the exit interface. So let's actually draw this out just to get a little idea of what we're expecting. So let's say, for example, that the destination network, which is 172.16.3.0/30. So let's put that network here, 172.16.3.0/30. So the network is somewhere here. And what it's saying is if we are on router 3, for router 3 to reach this network, which is 172.16.3.0/30, it needs to go through 192.168.10.5. So let's put router X here, and let's put, well, it's a serial cable. Well, the connection is serial 000. So let's put a serial connection here, and this IP, which is 192.168.10.5, that IP is going to be right here, which is 192.168.10.5. And this interface is going to be serial 000. And somewhere there, the connection is made. So what we are saying is if router 3, which is currently our router right now, if router 3 gets a packet that is destined for 172.16.3.0/30 network, router 3 is going to forward that packet to 192.168.10.5, which is router X here. But to be specific, it is going to forward it out of this interface as well. So router 3 knows the next hop, as in the next router to forward it to, and router 3 also know which of its interface to actually use to actually forward that packet out of. So it knows the exit interface and it knows the next hop IP. And of course, it knows how long this route, this entire route, has been installed within the routing table. Please keep in mind that only dynamic routing protocols will have a next hop IP within the routing table. Each dynamic routing protocol has a very special number assigned to it. This number is called the administrative distance. The administrative distance is simply used to determine what we call the trustworthiness of a route or trustworthiness of a routing protocol. So therefore, the path or the routing protocol that has a path to a destination network that also have the lowest administrative distance will be chosen, and that route will be installed within the routing table as the preferred routing protocol. The thing is, the administrative distance always takes priority. So now let's take a look at the default administrative distance that is used on Cisco routers. So these here are the well-known administrative distance for each of these routing sources and routing protocols. So a directly connected route has an administrative distance of 0, which is technically the highest in terms of priority value. A static route is normally installed manually by a network administrator or a network engineer and has an administrative distance of 1. eBGP has 20, EIGRP 90, OSPF 110, RIP Routing Information Protocol 120, and IBGP 200. So this means to say that, let's say for example we have a router, and let's call this router 1, and let's say we have a destination network. So let's put X here as our destination network. And let's imagine that there are two parts to the same destination network. There's part A and part B. If part A has an administrative distance of 1, let's put 1 in brackets, and B has an administrative distance of 5, well, the part that has the lowest administrative distance will take precedence. So therefore, because part A has an administrative distance of 1 and B has 5, the router will choose part A to forward its messages to network X. The same concept applies here. Within a router or within a Cisco router, you can have multiple routing protocols operating at the same time. And each of these routing protocols may actually discover a possible path to a certain destination network. What if you have 3 routing protocols that discover a same path to the same destination network? What actually breaks the tie? Well, the routing protocol that has the lowest administrative distance will be chosen as a preferred route for that specific destination network. Within the routing table, we always have an X/Y value that is between square brackets. This is as long as we are using a dynamic routing protocol. So for example, without looking at the source codes here, simply by looking at the X value, which is simply the administrative distance value, we need to know what the routing protocol is. Example, we can see across here, which is the X value, here and here, which is the X value, of course. These X values simply indicates the administrative distance. And 110 simply equates to, or simply refers to, that this route has been learned and installed by the OSPF routing protocol. If we take a look at the actual routing source, we can see it also says O. And remember, O is for OSPF based on the routing source codes in the Cisco routing table. Another key component is the metric. So what if you are only using one routing protocol? Let's say the routing protocol is OSPF, and OSPF found 3 possible routes to the same destination. How will the router choose the best path? Well, this is where the metric comes into play. Each routing protocol uses their own algorithm to calculate the metric, or in other words, the cost for the best path to a destination network. There may be multiple paths to a destination network. The metric is used to determine the most suitable path for a routing protocol. For example, RIP uses hop count, but RIP has a maximum hop count of 15. So therefore, since RIP has a maximum hop count of 15, it simply means that on a network that runs RIP, you cannot have more than 15 hops between your source and destination. OSPF uses the cumulative bandwidth between a source and destination network, while EIGRP uses what we call the K values or the K weights, which is bandwidth, delay, receiving load, transmitting load, and the reliability of the link. However, EIGRP uses primarily bandwidth and delay to actually calculate the best cost to reach that network. So to put simply, the cheapest cost of a routing protocol to a particular network, that route will be installed within the routing table. But always remember, the first thing is considered is the administrative distance, and once a suitable, well, let's say an actual routing protocol is chosen, then Within that routing protocol, the route with the cheapest cost or the least metric will be used to implement the route within the routing table. And if you recall, we were speaking about the x/y value within these square brackets. Well, the y value simply represents a metric. So remember, the x value is first and then there's a y value. The y value is the actual metric. So depending on the dynamic routing protocol, each of these, their algorithm uses a very unique element to actually calculate the metric. But overall, the metric is simply the cost to reach that particular destination network. One of the most important elements within the routing table is known as the gateway of last resort. The gateway of last resort is simply the default route that is actually configured on a router. Yes, a router needs a default route to reach, let's say, a foreign network, or let's say an unknown network, such as the internet. So to put simply, a default route always points towards the internet. But when configuring a default route, you need to tell the router how to reach out to the internet. And that's where the importance of a gateway of last resort comes in. So default routes are used to direct packets addressed to a network which does not explicitly is listed within the routing table. So let's take a look at how we can interpret the gateway of last resort for a router. So let's take a look at this routing table. Looking at a routing table, we can see a gateway of last resort is set. So let's imagine this router is, let's say, B3, right? Just randomly, B3. B3 has a gateway of last resort, and the gateway of last resort is 192.168.10.9 to network 0.0.0.0, like four zeros. So what does this mean? Well, what if B3 got a packet that is destined for a network that does not belong within this routing table? So let's say it got a packet for, let's say, 10.10.10.4. Well, B3 is going to check its routing table from top to bottom, looking for a possible match in terms of a destination network for 10.10.10.4. Well, looking at a routing table, it's checking from top to bottom, but it is unable to find 10.10.10.4. Well, a destination network. But looking closely here, it has a very special network, which is a network ID is 0.0.0.0 subnet mask 0. And it is saying via 192.168.10.9, which is also the same address up here. And that network is connected to serial 001. So what does this mean? Well, to put simply, this means that if B3 is unable to find a destination network that it does not have listed within the routing table here right now, it is going to forward it to its gateway of last resort, which is 192.168.10.9, and whatever this device is, it is going to take the responsibility to forward that packet to 10.10.10.4, to put simply. So if we clear this up just a little bit and let us just recreate this once more. So we have a router, let's say it's B3, and B3 has a gateway of last resort, which is connected to, according to this, serial 001. So let's put router A here, right? And router A is connected to, let's say, the internet. Just saying it's the internet. And since it's a serial interface, we will use our zigzag line. And this is serial 001. So this is serial 0/0/1. The gateway of last resort is 192.168.10.10, also indicated here. So that's this address right here on A. So let's say, for example, we have PC1. across here. Let's say there's a switch and everything is connected like this. PC1 wants to send a message to a particular device. Let's say the device is 10.10.10.4. Well, PC1 will forward it to its default gateway, which is B3. And B3 is going to check its routing table from top to bottom. Now, in this routing table, we are not seeing a network for 10.10.10.4. But there's a special network which is all zeros, and the subnet mask is all zeros. And this simply indicates that, hey, if you're unable to find a network, I will accept the packets for any network that you do not have and forward it to this address, which is 192.168.10.9. And even up here too, like where it's highlighted, it is saying the gateway of last resort is 192.168.10.9. So therefore, B3 will still accept the message that is destined to 10.10.10.4 and forward it across to A, because A is the gateway of last resort for router B. And A will check its routing table and determine how to forward that message. Typically, we'll create a default route that points towards the internet, and we'll specify a next hop IP as part of that route. And that's how you're able to quickly identify the gateway of last resort on a router, because all of this is done within the routing table, which is using the show IP route command all the time. So having completed this video, you have learned about each component within the routing table of a Cisco iOS router, and you have also discovered the purpose of the administrative distance and the use of the metric. In the next video, we'll take a look at how a Cisco router makes its forwarding decision. I hope this video has been informative for you, and I hope to see you in the next one.